According to the Threads and Spinons theory, the nucleus is bound together not by a conventional strong nuclear force, but by an intricate field of threads and spinons. These threads create a stabilizing lattice that interweaves around the nucleus, forming a dynamic structure that dictates atomic cohesion and stability. Unlike traditional force models, this framework suggests that nuclear integrity arises from the equilibrium of thread tension and spinon interactions. As nuclei grow larger, the tension within these threads becomes increasingly difficult to sustain across a greater volume. This results in a progressive weakening of the stabilizing field, explaining why larger atomic nuclei exhibit greater instability and are more prone to decay. This aligns with empirical observations in nuclear physics, where heavy elements tend to undergo fission or radioactive breakdown due to insufficient thread cohesion. Electrons, rather than existing as discrete particles in fixed orbits, are manifestations of thread dynamics, behaving as a code-like structure akin to cotton candy. Their charge stability emerges from their continuous adaptation within the thread cloud, which governs their movement and interaction with the nucleus. This challenges traditional quantum orbital models and suggests that electron behavior is dictated by the tension and distribution of surrounding threads rather than electrostatic forces alone. To mathematically describe the strength of this binding structure, we introduce the binding strength equation. This equation highlights a critical relationship. As the nucleus grows, the denominator increases, thereby reducing the overall binding strength. This aligns with the observed instability of heavier elements. A higher thread density, D, or stronger thread tension, T, reinforces nuclear cohesion, whereas an excessive nucleon count, N, dilutes the stabilizing effect, making larger nuclei inherently more fragile. Thus, the stability of atomic structures is fundamentally governed by the intricate interplay of thread tension, spinon interactions, and nucleon count. This redefinition of nuclear cohesion provides a more comprehensive explanation for atomic behavior within the framework of the Threads and Spinons theory.